And this is definitely very collaborative work with Stefan Talca, Thomas Wall, and Fernando Pareja Roman's a recent postdoc in my group, and many others shown here. All right, so we probably, many of us have tried to go to community meetings to talk to people about flooding, and this was my experience with that. And at the Howard Beach Motorboat Club in Hamilton Beach, neighboring Hamilton Beach, South Queens, on a sunny day. This is just about a 4.2-foot water level, and not even the minor flood threshold, which is about 4.4 feet, but it's called the near flood threshold, which I don't know if they have that for all stations, but it's a rising occurrence, and we all know, we've all seen this too, exponential growth in floods. It's doubling at this location about once every decade, with a clear rise since for the past 30, 40 years, now to where there's about 50 floods per year. Of this elevation, there's about 15 or 20 minor floods per year in Jamaica Bay, at that slightly higher elevation. But and what I'm going to talk today about is looking at this sort of attribution to sea level rise. You might assume this is a sea level rise driven problem entirely because of the exponential growth, and that can be land subsidence and obviously global or climate change driven sea level rise. But this is a case where it's also, very few of these floods would be occurring without landscape change also in this case. And a lot of this work was motivated originally, or some of this work was motivated originally by our discovery in New York Harbor, work led by Stefan Talca, where his recovery of data from around the heart of New York Harbor shown here. I think there's one station that's a little further out, Sandy Hook, but corrected to based on the existing overlapping data, corrected to New York Harbor. And this is all the annual maximum storm tide, each bar, without sea level rise, with sea level rise taken out. So we've found, and we still haven't explained why there was this increase in storm tides over 180 years. And so it's still a mystery. There's been studies looking at, we know that there was a pretty strong NAO relationship, so the climate variability had a role to play here, but there's been no evidence that the climate changes to storms have driven this rise yet, and even a reconstruction of the historic bathymetry of the bay, not including the floodplains actually, but Dave Ralston and Stefan and others didn't find much change to at least the couple storms that they ran, Sandy and one other, I believe. And then I've done AdCirc flood model experiments where I eliminated the landfill in kind of a coarse way around the harbor to see if that on its own could, taking away that storage area for floodwaters to go into might lead to the waters, reaching a higher peak elevation. But again, not really solving this mystery. So, but this kind of, problem has led, this general topic of trying to understand if it can be climate or geomorphology is the focus of our, a lot of our work the past, I'd say about 8 years, focusing now toward a project we're funded 2 years now under the NSF Prevents Prediction and Resilience Against Extreme Events program. So Stefan and David J. put together this nice figure in Annual Reviews in Marine Science that summarizes, that all these many changes that occur in estuaries. In addition to the offshore boundary forcing of sea level changes, potential storm changes, et cetera, and also the inland changes in river flows, which can be substantial for a lot of places. There's dredging effects, there's removal of geomorphic features like a separate channel, landfill, dramatic changes affecting estuaries that can lead to altered reflection, altered choking, and I'll come back to these terms later on, of a tide or a storm surge as it enters a bay, meaning the effect of friction reducing its size as it comes into the bay, like a choking of air, for example. So there's all these changes going from historical systems on the left to the modern, more streamlined and deepened estuaries on the right. So the objective of this research is to reveal and contrast the mechanisms by which climatic and geomorphic changes alter flood risk, and to learn how to separate these two effects is one of our long-term goals. And so today I'm going to present on these four main topics: statistical modeling example to demonstrate and quantify the effects of changing tides on U.S. nuisance flooding. Dynamic modeling to quantify the effect of anthropogenic sea level rise on Hurricane Sandy's flooding damages and affected population. And those are two different published papers. Then dynamic modeling for flood attribution to geomorphic change alone, and also looking deeper at the mechanisms for Jamaica Bay, New York City, an area that's had a lot of dramatic change in its geomorphology and resulting big increases in storm tides and tide range. And lastly, I'll briefly talk about and show some results on spectral analysis, where we're trying to look at the differing signatures and transfer function and spectral response of a bay relative to the offshore water levels. And there we're trying to think about how we can, instead of having to dynamically model a system with the historic data and the modern data, how, whether or not there's ways we can separate out these different effects without having to create a dynamic model, if we can just use the data and have some understanding of different kinds of estuary systems. The motivations here are, first, to build consensus on, as many of us, I think, to build consensus on climate mitigation by attributing its effects and its damages. Second, to improve climate adaptation by improving our understanding of what is actually worsening coastal flooding, be it climate change or something else. Next, quantifying and incorporating different types of non-stationarities. If we want to have a risk assessment, we want to typically remove from all the historical floods, remove the climate change or remove the sea level rise effect. And it gives us a better, more consistent sample. Well, if there's also been dredging effects, then it could be good to remove those effects to have more of a consistent sample of what a storm surge can be based on those historic data. And also we can better understand the potential uncertainties in the future if we know about the past changes better. And those can include dredging, for example, or if a port is closed, allowing a estuary to sediment in and reversing all those historical dredging effects. And lastly, I think there is, potential that this kind of research could help improve detection of climate change impacts, such as on storm surge, if we can identify and remove these other factors. All right, so I'll jump in briefly reviewing a few papers published in the last year. First, the statistical modeling approach to detecting how changing tides have influenced flood frequency. So what's done, the methodology here is we use tide gauge data, the blue time series, which is mostly covered up, but that's the raw actual data set. We go to the very furthest back data, in this case around 1910, and we identify the historic tide condition. And with harmonic analysis, we can represent what the frequency content of the tides was then. And also we do deal within this whole analysis with nodal variation also, based on a model of the nodal variation. So then we project that historic tide all the way forward into the future, and we also, for every year through the time series, take out the tide from the observed data, and we put back in the historic tide for that year. So it's sort of a tide replacement approach, where we can take out the tides as they occurred and stick back in the tides as they would have occurred with the historic tides from, say, 1910. So here it is. We remove the observed non-stationary tides that have been evolving, and that's the blue curve where you see the tides are getting larger through the time series. We replace it with the stationary historic tides. That's the red curve. So it includes storm surge. Any non-tidal anomaly isn't changed, only the tides.
Hello, everyone.
Are replaced with the historical.
Philip, sorry to
2.71.
interrupt you.
Yes.
I lost you then for a second.
Yeah, I got a message. My internet connection unstable. Just let me know whenever that happens, and I don't know what we'll do about it. But I'm at a university, a tech school. We're supposed to have better internet than this, but hopefully it doesn't go again. But occasionally that happens.
Okay, just
All right,
want
so
to
I
check
was
it
just
was.
saying the distance of mean high water above mean sea level was 0.53 meters in about 1930, and now it's 0.71 meters. So they're not huge changes in tides, but that's a tide range increase of about a foot, 17 centimeters times 2, so 34 centimeters. So the results looking around the country show, and so there's differing symbolisms here. One is the colors tell you the aggregated number of increased days or decreased days. Red is increase and blue is decrease. And so it's 40 tide gauge locations where there's enough data, historical data, that the analysis was done. So generally these are NOAA stations. And there's different symbols for estuaries versus inland areas. So the circles are the coastal areas, and the triangles are within estuaries. So one example of where you see there's been big increases, one pattern here you'll see is that the estuaries often show the large increases, but the coastal stations like Atlantic City or Fort Pulaski that are nearby them don't show these increases. So Philadelphia
Oh, sorry, everyone. It looks like
versus Atlantic City, so you have a big increase that are driven by, did you lose me again? No. That are driven by these changes in tides. And you don't see that at nearly as many of the coastal stations. It tends to be primarily at the estuary stations. And now looking at this another way, and I'll try to summarize this briefly so as not to blind you. The increase, cases in red are increases in nuisance flood, and it's going through time, a time series on the x-axis from 1950 to 2020. And then it's all these different stations. And at the very top is just the cases that have had the most increase in nuisance flooding due to tide changes. And at the bottom, cases actually had a decrease, such as Washington, D.C. I'm not sure the answer why Washington, D.C. had that decrease, but I think it may be due to a bridge that was built that actually damps out the tides just downstream of D.C. And in some of these cases, it can be other changes such as to river flow management and things like that. But what we often see, so the cases that are most extreme are Wilmington, San Francisco, Philadelphia. They tend to be places where there's been a lot of dredging and maybe there's a long channel that's where the depths have been doubled or tripled. So and historically, because of that long channel that was shallow, there was a lot of frictional effect that would damp the tide through dissipation. And now it's much deeper. It can also be, and this may be the case in San Francisco, where because of all the deepening and because of hardening of shorelines, there's more reflection of the tide. And so the tide may have an amplification through reflection or through resonance effects. So you do see some cases with very large increases. So in net, over those 40 NOAA stations, there's been a 20% of the increase in floods has been driven by changing tides. So it's pretty significant impact in net over 40 stations. Something like 20 of those had increases. 17 or 19 cases have had increases. So you saw those cases in red. And for those stations alone, just looking at those, it's about a 27% more floods than you would have if you hadn't had these historical changes in tides. The effects are strongest in urbanized estuaries, and you can often trace this back to anthropogenic impacts, changing the geomorphology, typically through landfill and through dredging, for two main examples. Our analysis is restricted to locations where we have a lot of historic data, but Stefan Talka has recovered, he's been working with trying to recover more data from USGS, which I think is now in the GESLA database with a recent update. Also, he's been recovering tide range data, so it's even when there's not actual tide time series, he and a student or postdoc funded under our project have been looking at how to use just tide range data that goes back even further. To try to extend these kinds of analyses to better understand a much more wide variety of stations, such as lagoons and places that aren't ports that typically have the deep, the longer historical time series.
We have a question in the chat. Sorry to interrupt you. From Vivian. She's asking, can you say something about nuisance flooding in Miami?
Yeah, well, we're almost that same work. We have a paper coming led by Francesco De Leo as part of our project and supervised by Stefan where I'm also playing a role, and Thomas Wall is also playing a role, where we look at Miami. So it's a good question. I don't know if if that's coincidental, but Stefan recovered some, there's not a very long history of tide gauge data for Miami, but there are some tide range estimates from around 1900 before all the dredging occurred. So that paper looks at how much of the flooding seen in Miami today could be due to the massive dredging of a port, where there used to be much smaller inlets. And that's kind of a widespread story, and so part of the story is obviously sea level rise, but part of it is likely dredging and basically blowing out a huge inlet for cruise ships and for a big port. And we see that along for a lot of the lagoons along Florida's coast. There's even one, Port Everglades didn't even have an inlet. And now it has a very deep inlet, and there's a lot more flooding in that section of the Florida coast. Fort Lauderdale area, they have a lot of flooding problems. So yeah, I think that was the one question. All right, so next paper I'll talk about is this one led by Ben Strauss with a large supporting cast, including myself, just published in Nature Communications. So here we're looking at attribution of anthropogenic only sea level rise, anthropogenic climate change only sea level rise. So it does not include anthropogenic water storage, for example. So in this work, my main role was involved with the modeling of water and damages. The water modeling at first was done at Stevens with myself and Sergei Vinogradov. In the end, we wanted to capture the whole Sandy affected area with the best flood model we could get. So Chris Massey at the Corps of Engineers worked with us on that. We validated, obviously, the flood modeling results. We created a spatially varying bias correction. Climate Central led that. And then we applied that for all of our simulations, but we ran many different simulations with a 20 centimeter range of different sea levels to kind of have an ensemble approach. So here now you're going to see the flooding occurring during Sandy filling in a lot of these floodplains. Not dramatic, the floodplains are much larger, and worse floods, it could make an even larger flood. Let me just stop on that. But there are places like Hoboken, Jersey City, basically filled up with 6 feet of water, all along Rockaway Peninsula. Many people unfortunately passed away in Midland Beach on Staten Island, where they were overtopped. So there's a lot of these low-lying neighborhoods that had some kind of berm that got overtopped, and suddenly they had 6 feet of water. And so it's a case actually where the expansion of the floodplain wasn't dramatic with sea level because of sea level rise, but the water was a lot deeper, and there was some expansion of the flooding spatially. So, and as I mentioned, there was also damage modeling that was done by Hans de Moel from the Netherlands using HAZUS MH. All right, and then in terms of sea level rise methods, the leads on this were not myself, but I'll do my best to explain and answer any questions. Ben, it's Strauss, Kopp, Bitterman, and Guilford were the leads. So the method is multi-method estimates for global and New York area anthropogenic climate change driven sea level rise from 1900 only forward to 2012 when Hurricane Sandy occurred. There's a budget-based approach, mostly mimicking what was done by Michael Oppenheimer in 2019, a semi-empirical approach that treats sea level as a function of temperature, similar to what Bob Kopp and others did in their PNAS study in 2016. Both approaches, and so I'm very briefly summarizing these, both approaches localize anthropogenic climate change driven sea level rise to only New York region, and that was a big challenge for the work. And they, as I mentioned, they omit anthropogenic water storage. It's just anthropogenic climate change effects. And all these estimates were combined in an ensemble simulation approach similar to that Kopp et al. 2016, but including both methods, and then that was the way that the uncertainties were merged. And the results of those sea level rise estimates globally and for New York are shown on the left here. So anthropogenic climate change driven sea level rise of 10.5 centimeters central estimate with a 6.6 to 17 centimeter 90% confidence range. And if just localized to New York, it's about 90% is large, and it's 9.6 centimeters. So about 10 centimeters of sea level rise back to between 1900 and 2012. And then based on the modeling of water and damages, We found about $8 billion out of the $60 billion was attributable to this additional sea level rise. Of course, we're omitting any, this is all conditioned on the storm already existing and the storm not changing. So that's a big unknown, is whether or not the storm's changes also made the event worse, but we're just looking at the sea level rise component. And it's 70,000 more people and 36,000 more buildings were flooded. All right, so next topic, now I'll get a little bit deeper into these topics. First, and mainly looking at geomorphic change and also its mechanisms for causing storm tides and flooding to change. And so there's one published paper here and another one in preparation. The published one's in Natural Hazards Earth System Science. And the in-prep papers, we're looking to go to JGR probably. And the first one will be more on the storm tide changes, and the second one more on the tide and nuisance flood changes, and more looking at how we can separate the climactic and geomorphic effects. So in my work, I often focus on Jamaica Bay because it's an area that has these shaded areas show the floodplains below 5 meters, and they show their population density within those floodplains. Jamaica Bay is an area with JFK Airport, and it's got just a lot of moderate to high density populated areas in its floodplains. The methods I'll use behind this next work is, we use digitization. Actually, Eric Sanderson and others were involved in this work. I should have credited him also at Wildlife Conservation Society. So digitizing the historic bathymetry data, which is surprisingly good quality back to the 1800s. Also archival tide gauge data recovery by Stefan. Model validation. So we basically create an estuary model of the 1870s and a modern day one, both flood models. And then simulations with different landscapes. For the storm tide characterization, it's 144 different storms, tropical, extratropical, simulated on both landscapes. And then 35-day tide time series to better understand just the tides. And all these simulations here are done with a modern sea level, so we're just isolating the geomorphic change effect in this case. So here's the landscapes and how they differed very dramatically. There was sort of a mission to improve the environment back in the early 1900s in this area, in a lot of the U.S., I think, and still really ongoing in some parts of the world, where the impression was that wetlands were something that was a waste of space, and they wanted to make a port out of over on Long Island. It never came to fruition, but the system was completely dramatically changed, but there is no port, and there's barely any shipping, but now we have a 1 kilometer wide, 8 to 15 meter deep inlet, whereas historically it was a much narrower and shorter, and on average shallower inlet. And obviously the floodplain is completely transformed. It went from being a high marsh mostly to being airports, 2 different airports, one that's no longer used, being neighborhoods. So really dramatic changes in the system. And then the tide data that Stefan recovered, which was basically in tabulations, of hourly water levels only during daytime. It presents its challenges for tide analysis, but this was really valuable for validation of the model. And we also validate the modern day model during Hurricane Sandy and for tidal conditions using USGS gauges that are in the bay. And so by simulating these 144 storms within a framework and based on past published work on New York Harbor with storms of all different sorts, we have a probabilistic assessment that enables us to estimate all different return periods, obviously. But this is just showing the 100-year return period for the historical landscape. Peak water level is about 2.4 meters. And here's the modern landscape. So same sea level, but different landscape, and the same boundary conditions, but completely different interior bay results. So it's about a 28 centimeter increase in the 100-year flood. Not dramatic, but the system used to damp the 100-year flood, and it got smaller from outside the bay to inside the bay. Now it amplifies it. And And so that's a pretty similar increase. I'm not showing it here, but we do simulate the climate change or the sea level rise impact on the same flood, and it's about the same increase. It's a very linear effect, the sea level rise effect in Jamaica Bay on the 100-year flood. So it's also about a foot increase in the 100-year water level due to sea level rise since the 1870s. All right, and so I've mentioned the inlet being changed dramatically, and so that, for me, that got my attention to look deeper into the lagoonal estuary literature. And there's been a lot of work done on that looks at this choking number and how tides can be choked out and shrink going into a bay. And these are driven. There's an increased damping or choking, which lowers the choking number. Actually, it's a little confusing, but a lower choking number means more of a damping. The drag coefficient, so friction, can enhance the choking. The inlet width, if it's length or the depth, they all influence. They can all lead to weakened choking, or if you shrink those, then a greater choking. The amplitude of the wave coming in, obviously there's stronger currents if you have a larger tide or a larger storm surge. So a higher amplitude can lead to greater choking. And these are all identified with their different exponents in this equation. The dominant case is the water depth, so the dredging really should have a very big impact. Estuary surface area is another factor. If you have a larger surface area, then there's more floodplain, and that can lead to more of a choking effect, a smaller tide in a bay if there's not time to fill the bay, for example. And that has a exponent of 1 when you multiply 2 by 1/2. So, but also the other thing I'll take note of here is the time scale is a factor of 1. So the time scale, if it's a diurnal tide, then it's choked less than if it's a semi-diurnal tide. Or if you have a really rapid storm surge event, then that could be choked a lot more because it has a very short time scale. So looking at some different cases for typical tides, we estimate that there's been about a 2.5 increase in the choking number. That would mean a lot less choking for tides, and I'll show some more results reflecting that in the next slide, next slide. And also for a large amplitude, short time scale storm like a Category 3 hurricane, once one hit New York in 1821 with about a 4-meter storm surge, but lower flood level than Sandy. That's also a similar, about a factor of 3 increase in choking of that event. So for extreme events or for tides, there appears to be a choking effect for this system. And we've definitely reduced the choking effect historically to where with tides, there's pretty much no choking effect. But even with an extreme storm surge, there could be a choking effect. Looking at tides, here's the case of the 1870s landscape. Both cases have the same sea level. 1870s landscape, you see basically a reduction in the tides along this transect going into the bay. And in the modern system, you see an amplification of tides. So some of the largest tides in New York City, apart from Western Long Island Sound, the largest tides in New York City are in Jamaica Bay. And it's largely a man-made problem by these landscape changes, is what we demonstrate here. And this transect is important here because we did analyses for this paper. I'm just going to show a quick snapshot of one of the analyses. It's the reflection coefficient. So there's, I don't remember who originally published this method, but Fernando found a method for taking the transect of water levels and tide amplitude and backing out how much reflection is occurring at the head of the bay. And so what we see is reflection factor. If it's perfect reflection, it's 1. If it's 0 reflection, it's 0 on the x-axis. Amplification of tide relative to the offshore boundary out at sea versus at the head of bay is shown on the x-axis. So the historical system had damping, so the amplification factor is below 1. The modern system has an amplification of about 15%. For these different tidal constituents, M2, N2, and S2. So, and we see a really strong relationship. So this is in this most recent work that's still not published, but we've been mostly looking at that choking effect, and there's some overlap between the choking effect and this reflection effect. If you have, if you eliminate the floodplain, your choking effect, as I mentioned, because the area of the bay is important, the floodable area, then it affects the choking. But also it affects the reflection. If you have a wall, as I showed in some of these plots here, you basically went from having a big floodplain to having a wall and an airport that reflects the tide really efficiently at about a reflection factor of 1. So immediately where the reflection occurs, you're doubling up the tide. But then as you go further back into the bay, the phasing of the reflected wave and the incoming wave are not perfectly in phase, so it's less. So it doesn't double the tide in the whole bay, but it does amplify the tide. And that's a good way of understanding why. And I'll say one other thing about reflection. I mean, we know about reflection due to places like Long Island Sound, where there's quarter wave resonance, are famous for being resonant, but really a lot of it is just about a reflection. And the reason why it's called quarter wave resonance is because the reflected wave completely at a nodal point at the beginning of the bay leads to there being 0 tide range, and then there's a doubled tide range at the reflection point. So it's really a relative thing, but again, this is just about Long Island Sound's a good example where there's a reflection of the tide that's nearly complete, very strong reflection, and it leads to very big tides. So reflection is something we don't want in these systems. So to summarize, and almost done with my talk, another few slides after this, summarize what we learned about geomorphic effects and the mechanisms. Landscape change since the 1800s for Jamaica Bay, increased storm tide elevations. We see these same patterns in many other places like Savannah, Georgia. We're working on some research about Savannah. We see it for Wilmington. We see it for St. Johns River, Jacksonville. Like I said, we also see some effect of geomorphic change for Miami. So we have a lot of different places we're looking at, and these changes in some of these estuaries, some estuaries there's very little effect, like New York Harbor. We don't think there's been a big effect on storm tides, but some of these systems we see big changes in tides and storm tides. The tides are amplified in 2020 Jamaica Bay, but were damped in the 1870s landscape. The choking effect at the inlet has been reduced. This reflects less dissipation in the inlet and tidal channels. It also reflects less area of floodplain in the bay. And then the last point I showed was that the reflection historically was only partial, about a 50% reflection, and now it's nearly 100% reflection of the tide wave. Okay, so the last thing I'll speak about is how we're using dynamic modeling and then also spectral analysis, analyzing the data we can create in these alternative realities of historic landscape and modern landscape, separating out sea level rise effects and geomorphic effects, and using spectral analysis to study whether or not we can detect separate signatures of climatic or sea level and geomorphic effects. So the methods are, first, I'll show results from a 1-year simulation of water levels for Jamaica Bay with the actual present day conditions with counterfactual sea levels, removing the climatic effect. So it's not the anthropogenic climate effect, it's actually the full non-land subsidence effect, and calling that climactic. That's 23 centimeters lower back to the 1870s. And then also the counterfactual landscape of the 1870s. And then I'll show the results of power spectral density and transfer function, representing the water level transfer amplitude change from offshore into the interior of the bay. Just brief summary of the results before I show a plot of the results is that the modeled number of floods for 2020 was 15. The number of floods without climatic sea level rise was only 1. And the number of floods without geomorphic change was 2. All right, and so here's a frequency distribution or probability distribution perspective. On the left is the full probability distribution for these 3 cases, and on the right is zoom-ins to just the tail on the right side. So first, it's the control simulation. Second, it's the taking out the geomorphologic change. So it's the 1870s landscape with modern sea level, and the bottom left, or the bottom 2 panels, are just the sea level change effect of about 23 centimeters of climatic sea level rise. And so one thing that you'll see is the shape, the effect of sea level rise, looking from the very top panel to the bottom, doesn't change the distribution of tides much at all. It just shifts over the distribution. As I mentioned, it's fairly linear effect on tides and normal, conditions through the years, nor'easter storm tides, etc. But when you look at the landscape effect, there's a very different distribution. It's much narrower. So you're not getting the extremes of high water or the extremes of low water because there's a lot more frictional effects or whatever, choking effects. You're not getting the reflection effects that amplify the extreme cases. And when you look at the tail, this is not just number of floods, but it's the probability of hourly water levels to reach these values. So you see a lot of cases in the control, only a few hours in the year. And like I said, it's about 2 floods, 2 semidiurnal floods. In the case without the landscape change, and then the case without the sea level change, climatic sea level change, it's about 1 flood out of the 15 that occurs. So we look next at the spectral distribution perspective. Frequency of a sea level, signal, tides, for example, are really jumping out here on the x-axis, and then the energy on the y-axis. So what you see jumping out is the semidiurnal tides have a really strong peak. The diurnal tides have a smaller peak. You do also see overtides like the 3 per day, terdiurnal overtide, that these are created by friction. We chose not to go to higher frequencies and other overtides. We're most interested in these changes. So the sea level rise versus control shows almost no difference in the spectral density, but you see there's a real big difference in drop off for the higher frequency cases for the landscape change annual simulation. And on the bottom is the transfer function. So the transfer function represents basically like how the amplitude, I think if you take this square root of these numbers, actually, it's how the amplitude would change going into the bay. The square root of transfer function. So a transfer function, and for the transfer functions getting down to be about 0.5 for semidiurnal or headed toward diurnal, terdiurnal. And so that means that there's something like a 0.7 reduction factor going into the bay for those frequencies. And as you get up to a really high frequency, which might be a really intense, like, rapid storm surge event, there's about a 0.1 transfer function. So these are completely different signature. And I think that's really important here. Part of our goal in this research is to learn whether or not we can separate out these geomorphic impacts on tide gauge data from the climatic changes. And I think the challenge here is that the tides this is still mainly, at these tidal frequencies, you've got tides happening every day of the year, and that's really dominating the signal. And so you see there's like little peaks, and the tides aren't, as large. Mainly the semidiurnal tide here, it's not an extreme event. So, this isn't going to capture necessarily how an extreme event with a semidiurnal frequency with like a 6-hour rise period or a 12-hour storm surge period is going to be affected because you have a lot more choking and effect if you have a larger amplitude wave. So this may not be necessarily moving the ball forward a lot, but I think it sort of gives, just seeing this hugely different signature for geomorphic change effects versus sea level change effects is, I think, valuable. And so that's where we are now. We're the last thing I'd say is it's consistent. It's really the whole reason for this decreasing transfer for higher frequency is that the choking, it's very consistent with the fact that choking is dependent on the time period of the wave. So as you have a higher frequency wave, you're going to have more choking. So it's very consistent with that, and that's not something you see for the sea level rise effect. So my final conclusions, first, climate change, and in particular sea level rise, is causing accelerating coastal flooding. Anthropogenic sea level rise alone caused an additional $8 billion in damages and 70,000 affected people during Hurricane Sandy. Changing tides, usually due to estuary urbanization practices such as dredging and landfill, have increased U.S. nuisance flooding by about 20%. And that's just looking at today's, at one sample year of the present. It's not commenting on the whole aggregate increase in nuisance flooding due to those changes. So today's nuisance floods at these NOAA tide gauge estuaries have been increased by about 20%. by geomorphic change alone. Of the 15 minor floods in 2020 in Jamaica Bay, there would only be about 2 without geomorphic change and about 1 without sea level rise. So they're a similar effect. In future work, we're looking to, we're studying more estuaries. I'm hoping to do a much more regional simulation with many different estuaries altered to better understand. This is some people call Jamaica Bay a unicorn estuary, but it's a lagoon that's been completely deepened and developed into a hypothetical port. But we're going to look at systems like Delaware Bay and other systems like river estuaries that have very different tidal propagation characteristics, for example, and also have river flow, freshwater inputs that could make them more complex. So we'll look at some of the same things like spectral analysis of the changing water level data, and try to develop methods for separating sea level and geomorphic change effects. And lastly, one thing that I'm already doing is I'm running, and maybe I'll give a little glimpse of this since we have time, running attribution simulations in real time. We have a forecasting system for water levels at Stevens, and I can take the outputs from those at my boundary of my model, and I can run simulations for Jamaica Bay, and I can map how, yesterday's, this is actually October, but I did this in real time, the coastal flood for Howard Beach and Howard Beach Motor Club and Hamilton Beach, for that area that floods so frequently, would have been different without that 23 centimeters of climate-driven sea level rise. So also doing this same kind of work, attribution, and I can do the same thing for the historical landscape change. We could illustrate to people how dredging has been part of the problem for their flooding. It has a similar, not quite as much of a reduction in flooding, but it's not just the sea level rise problem for Jamaica Bay. It's also this historic landscape change problem. And we can illustrate that to people in real time when there's a flood happening. So that's the last thing. And I think I'll end there, and I'd be happy to answer any questions.
Thanks ever so much, Philip. That was fascinating talk. So I'm going to dive straight in. We've got a question in the chat from Gavin. I'm going to pick on him and ask him if he wants to unmute.
Yeah, thanks, Craig. So I mean, could we not just solve the Jamaica Bay problems by filling in the inlet then?
I've proposed to, they're planning on, they're looking at, and they're likely, I think, at least 50% chance that they're going to build a barrier across the inlet of Jamaica Bay within the next 10 or 15 years that has gates and just make it more unnatural of a system. And the most powerful locals support it because they have very severe flooding problems, and those most powerful locals live on islands in the middle of the bay. And they wield a lot of power, and so I have proposed to try to have a restoration of Jamaica Bay that reverses all the historical changes in the channels. You can't change the fact that there's 100,000 people living in the floodplain, on top of former marshes. But I definitely pushed for a while on this topic. Yeah, what's that?
Have you modeled that?
Yeah, we've modeled, yes.
And it does reduce the flooding in a similar way to restoring the 1870 plain?
Too bad I don't have it handy right now, but you can, if you shallow the bay in a tapered way that's not completely unnatural, so that the inlet's about 4 or 5 meters deep instead of 8 to 12 meters deep, and you fill in the borrow pits that they dug out to build the airports, then you can't stop the 100-year flood, right? And that's one of the reasons why the Corps of Engineers isn't looking at this anymore as an option. It's one of the reasons. Like I said, there's also public opposition to dramatically changing the bay, right? To having a dramatic restoration wasn't something that caught on. But it's definitely something, and the additional, so you can reduce the flood area by about 50% if you have this dramatic change, and it would require a massive amount of sediment to be put into the bay from some source, right? So, and that's not an easy problem to solve either. It would take a large quantity. But you can also reduce the hypoxia problems that they have because you're shallowing, a borrow pit that's been dug out that's not natural and that doesn't circulate very well. So there's hypoxia problems that could also be addressed. So it's something that, has been put out there and studied in public processes, co-production process with communities, and it kind of got pushed aside. The one thing that did get kept and studied more deeply was an idea of narrowing the inlet. But as you saw from that choking number, the depth impact's stronger than the inlet width impact, and the choking, wasn't very impactful with narrowing the inlet. So, one of the things they really care about there is their striped bass fishing, and they don't want the deep channels and the cold, deeper water that the striped bass seem to like to go away. And they're also very skeptical of government intervention with sediment, putting sediments in the bay, because historically there was some plans to put polluted sediment in the bay. So,
Okay, thank you.
It's definitely been tried out. And
just quickly, do you have an idea of the cost of putting sediment in the bay compared to putting across a barrier? And then we should go to John. Sorry.
I really need to publish this paper. Right? This is all in a paper. It's all in a 2016 report. That we, and we the normal cost for sand, offshore sand, for beach replenishment or any purpose, is pretty high per cubic yard. But I interviewed somebody from a dredge company, and we came up with a price, and we found it's like order of $1 billion for getting all the sediment to fill in the bay, but that's a really rough estimate. And the surge barrier approach is more like $5 billion. You have levees and a barrier at the entrance. So it's something that could be cost competitive. I'm going to keep moving forward and keep trying to push it. No decisions have been made, and until Congress budgets funding to build an engineered infrastructure, it's not done. So it could be a long time before anything is actually done, unfortunately, to help stop the flooding for these people.
Thanks. We have a question from John Crasting next.
Thanks. Yeah, this was a great talk. I'm coming at this from more of a global modeling perspective, but I was wondering if you could go back to your first results and think about, and perhaps give me some more information about how well the regional and estuary modeling are capturing dynamic changes in bathymetry as dredging goes through. Is this something we need more effort and focus on in order to understand the sea level rise question in more detail? And if we do have that capability, do we have good enough observational or reconstructed estimates of how coastal environments and estuaries have been dredged over time to drive that changing bathymetry?
Are you asking about, our estuary and coastal flood models, we trust them a lot when it comes to simulating tides and bathymetric changes effects. And they've improved dramatically in the past decade even. So even the models I'm using aren't the best models anymore, because the field's moving forward so rapidly. Especially due to hurricane, storm surge, disasters, for example. Now, were you asking if the global models can resolve it?
No, I was just thinking, I'm coming at it from the global perspective, so I'm not familiar with how much is being done on that estuary level. But I think you answered my question there. Do we have, I guess the second part of it is, do we have enough historical reconstruction information at this point to drive those hyper-local models?
We're working on it. And Stefan Talka is the person who does the most work trying to find it. He's tallied, if somebody had endless time, they could find all the bathymetric charts that existed in the 1800s and digitize them all. But it's a lot of work, and also connecting the bathymetry to the topography is a real, with the wetlands in between, is a real unknown area that needs better understanding. So we have to make some assumption about the wetlands elevation relative to tide datums, which is doable, but there's some area of uncertainty there in the DEM because nobody surveyed the wetlands, And Stefan's been trying to get together all the Corps of Engineers data or government data on inlets and how they changed. And so I think that's since we think this choking effect with the inlet and then also the Bay Area is really important.
Looks like Philip is frozen. Just give a moment.
we might be able to put together at least some of these basic parameters instead of wetland, landfill as separate factors and sea level rise. All these things sort of separate them out in more of an idealized way and better understand how different types of estuaries respond to these different changes. So the answer is kind of like, no, we don't have all that data, but we're working on at least trying to account for it better. You know, I mean, my wish, like I said, is that if we could see how different kinds of estuaries, geomorphic change effects influence storm tides or tides, you know, if we could understand the pattern, then maybe we can come up with a statistical way to remove that from tide gauge data, just like, you know, we remove sea level rise from tide gauge data, and, you know, to take out non-stationary, you know, factors. And that would be, you know, without having to do a dynamic model simulation of a historic system.
Thanks.
We have, I think, Vivian next.
Yes, would marsh restoration help dampen the nuisance flooding or tidal flooding?
In some places it can, but in some places it doesn't. You know, Jamaica Bay is an example. In a deep water port, it's of much less efficacy than in an area that has floodplains and people are living behind the floodplain. So you got rid of all those fringing, you know, reefs in Jamaica Bay, or fringing estuary, fringing wetlands in Jamaica Bay, and now people live on top of them on the waterfront because it was developed to be, you know, for people to be on the water, so they go, you know, they could jump in their boat and go fishing, or for commerce, you know, industry. And so there's no fringing wetlands anymore. There's only interior wetland restoration efforts, and because the interior wetlands are mostly gone. Those interior wetlands the water comes into Jamaica Bay and flows through these deep frictionless channels, more or less. So it goes straight to the neighborhoods, and it waves, you know, waves hello as it goes by the wetlands. It doesn't have to go over the wetlands. There's a little bit of an effect in an extreme event, because the water starts flowing in every direction during an extreme event. But for the most part, wetlands have been shown with our work and some other studies to not influence total water level at the neighborhoods. It can dampen the waves. And so we have had a paper, and the Corps of Engineers had a paper looking at how restoration of these islands and wetlands in the center of the bay can dampen the waves, and that can reduce impacts. But yeah, it's a particular problem, you know, is how do you reduce, you know, flooding for port estuaries, you know, and this is basically a port estuary. And same thing with New York Harbor. And nature-based solutions are less, you know, effective. And so, yeah, so that's why I was coming up with the idea of narrowing and shallowing channels as sort of a much more, you know, big thinking approach to reducing flooding. But again, that doesn't, you know, none of these approaches can stop a 100-year flood. And as long as that's the goal that our government has, that you must stop a 100-year flood to get the funding from the federal government, then, you know, none of these solutions are getting us very far. And we're going to resort to engineered, you know, barriers and levees and things.
I think next up is Klaus.
Yeah, Philip, I noticed in your tapestry slide where you showed all the harbors and the orange in the upper right and the blue in the lower left. There was one really striking exception. It was up in Maine. I'm not sure where it was.
Was it this one?
Yeah, no, the next, you just had it in a moment.
Yeah.
Yeah, this one. Yeah, in Eastport, Maine. What in the hell is going on there? Is there ice going on? Or?
Yeah, I don't know. That's a great question. I'd have to ask Thomas to remind me of that. I can't remember, but yeah, that's crazy. It's up and down. It's an ocean station. That's what the OCs are for. And they show that really the more extreme cases are all estuary stations. They're usually not the ocean stations. But, you know, Maine is in the Gulf of Maine, you know, Eastport's in the Gulf of Maine. And so there's a complexity that the tides there are
Yeah. Well, I mean, often you can learn from the
huge,
exception.
but I can't answer your question. very large, and their nodal variations are very, pretty significant. So it's a little more unusual place, but it's a good question. I encourage you to focus more on the bright red and the bright blue, or the overall pattern.
Okie doke. I think next we have just trying to get through people. Mike Steckler in the chat.
Yeah. So I was just wondering, when you showed that looking at the historic tides and carry them forward to the modern day to see where the changes were, is how long a time series do you need to be able to do that kind of analysis?
Well, if you don't go back, if you don't have any tide data before anthropogenic changes occurred, then you're missing out on capturing the natural tide, right? I think there was a minimum in that paper of something like 60 years, but I can't remember exactly. But you can, that's why it's nice that Stefan found there's a lot of tide range data from even when there weren't long-term tide measurements. So maybe you can go back to the tide range estimate like we did for Miami, and you can, and then you're going back before all the dredging occurred, and you can see, at least make a good estimate of what a tide time series would be based on the tide range. And that's some of the science that's going into this next paper. And you can do the same kind of analysis.
All right, I'll write to you about it.
Yeah, so you're thinking about some places that only have a little bit of data. Yeah, I mean, you need to have the pre-development, ideally, but you could learn about the past decade's impacts, right? If you just want to learn about something done like poldering, right, in Bangladesh, then maybe you could go back 20 or 30 years and you can learn about what's happened, how those changing tides have impacted flooding over 20 years.
I have tidal data going back to 77. The poldering was in the 60s and 70s, as only there's been analysis showing that there's been a tidal amplification since then. And I'm just wondering, better than the very simple analysis that was done.
Yep.
We had another point from Gavin in the chat. He's asked a question: do people realize that these geomorphic changes would impact the tides at the time that they were done?
No, I think they did not. I would say there's very limited understanding, of what it would mean. I think there just was very little understanding, or really, a whole different world, right? When they were going to improve Jamaica Bay by building, coal-fired power plants all around it and dredging it and turning it into a port. But yeah, I don't think they did. No, it was beyond their understanding. I think people naturally just see the water surface, and if there's green grass on it, they don't really think, a captain of a boat understands the depths of the water, but I don't think they understand the frictional effects. And there's a lot of physics here that I think people didn't understand. They did understand tide, harmonic analysis and tide. There were some smart people who understood tides well enough to compute tide datums when they made a map, right? So some of these data we have is because they've made a map and they wanted to know the datum, the mean low water datum, or, so that they could have a datum for their maps. And so that's one reason they collected data in the 1800s. So there was a lot of sophistication about some things, but not about how the tides might change, I think.
I think we've made mistakes going way back, because back in Ephesus, the Romans built a mole to stop the harbor from silting up, and it had the opposite effect. Yeah,
it's complicated. And part of the problem is that, it's the same thing when people build landfill on top of a wetland and build a neighborhood. They had no reason to expect sea level rise. There's no way to anticipate sea level rise. Even the land subsidence part of it that was always there, I think that was not in someone's perception, because the normal variability through the year of water levels is so dramatic. So, but then, you know, typically any landfill development was always just a few feet above high tide, normal high tide. So that it's just a common problem that people don't see, and that's because within, or really, it was probably more likely a foot above the annual typical flood, right? And they probably had a sense of that, but then, you know, Hurricane Sandy was about 6 feet higher than the typical annual flood. So we have an area here where these extreme events are so dramatic that I think there's no anticipation of that from our mayors or anyone, you know, or Ida's rainfall, same thing. You know, these extremes catch people by surprise, and that's also a part of the problem.
We're about 5 minutes past noon here. I should probably ask people if there are any final questions before letting people get on to other meetings and things.
So let me ask the final question. Very nice talk. I appreciate it so much. So can you give us any insight into the JFK runway? Did that have any impact on Jamaica Bay circulation and flooding?
Which one that they built most recently in the 70s or so? When did they last build a runway?
Yeah, well, I guess the present configuration is what I'm thinking about.
I know, and related answer, this will answer your question just the same, I think. There was a proposal to look at, you know, I think from Regional Planning Authority or whatever, RPA, to expand JFK Airport a few years ago, and it got shot down really quickly. But anything you do to shrink the bay, I mean, right now there's no choking effect in Jamaica Bay, so I don't think it would make things worse anymore. If there were a choking effect, then shrinking the bay eliminates the, you know, it reduces the choking effect, and growing the bay makes it stronger. You know, and that 1870 system had a choking effect that had an influence on the tides, and it damped out the tides. But in the modern day, all you have is a reflection, and I don't think the reflection would be made any worse by changing the airport.
Great, thanks. Nice talk.
Thank you.
Okie doke. Thanks everyone ever so much for joining us. Klaus is clapping.
Thanks, Klaus. Nice to see you.
Yeah, thanks ever so much again, Philip, for a really interesting talk. I look forward to uploading this to the interview. I hope you all have a great rest of the day.
Take care.
Thanks, everyone.